All right, we're going to do a video showing you how to code, create a code which computes the center of mass of a uniform rod. At first, this will be somewhat boring, but later on, we need this code so we can generalize it to non-uniform rods and other shapes. So stay with me, even if it seems like it might be a dry subject because it's a uniform rod. Let's start with the screen share. Okay, so I should be giving you a link to a starter code that has a lot of this here to save you some tedious time, but I left some things out so I would remember to say it as I go through. So in this case, we're going to create a rod. We're going to specify the length here. I'm going to specify the minimum X value for that rod and the maximum value. Now you might just say, well, dude, why didn't you just type in rod length here? Well, I've got some tricks. Basically, the idea is what if I change the X position here, then I don't need to change it again right there later. So this is a way to reduce mistakes if I change my code later. First, it seems silly, but yeah, that's what that's for. So next, mu, let's just type in a number. Let's just say mu is the linear mass density. Obviously, if you wanted to, you could calculate a mass per unit length or something like that if you had those, but I'm going to hit Control Z to get back there. So let's say we want to use this. Let's say n is the number 5, and let's say dx. Now this, we actually want to do the same kind of trick. So if I'm going to cut my rod into 5 chunks, I want dx to be the rod's length divided by n. Why are we doing it this way instead of just saying 1? Well, think about it. If I want, I could very easily change the rod length or the number of slices later without having to redo this line of code. So it saves me time later. Now, I'm going to create a visual guide here. And the idea is this is just a cylinder that's drawn on the screen to represent what we're trying to figure out. Now, in this case, we are not actually going to use this visual guide to do any calculations. So it's just there so you can see it. This new attribute called opacity is basically how transparent it is. If the level is 0, it's invisible. If the level is 1, it's fully opaque. So this is just going to be a ghost of a cylinder just to kind of tell where we're at. All right. And I've chosen to set the radius here. And notice it's kind of convenient to set these parameters afterwards so that your code doesn't just, it's just a little bit easier to read this way sometimes. All right. There's an XY axis. That's pretty straightforward. Now I'm going to create a parameter called numer. Actually, let me explain what I'm going to do here. In the center of mass formula, you probably know the integral formulation. So we know that x center of mass is equal to the integral of x dx, dm divided by the integral of dm. Now remember, the denominator here, this is essentially, if you integrate over dm, you get the total mass. So that's just the total mass on the denominator written in another way. We could actually rewrite this in sum notation from I equals 1 to n of x sub I, m sub I. You've probably seen it like that in a textbook once. All this divided by the sum from I equals 1 to n of just m sub I. Now, I want to point out, we can actually turn this into a vector. So here, x vector just means x in the I hat, y in the j hat, z in the k hat. So if I do that, I need to make this a vector too. Now, why do I mention that? Well, this method is useful for us, and it tells me immediately if I want the numerator of that fraction here, I'm going to make sure that that, is a vector. And let's specify it is 0, 0, 0. So that initializes the numerator, and just so I don't have to write the whole word, I'm calling it numer. The denominator, if you notice in that formula, is just the mass, so that's a scalar. So I'm going to initialize that with the value 0. And now I'm going to build a rod out of spheres and I want to keep those organized, this is going to help me. Notice the square brackets here, right? Not the curly brackets, not parentheses, square brackets. So this is a new thing. Rod equals an empty list. Okay. And now let's just say I equals 0. Now you might be saying, dude, you just said let I go from 1 to n. It turns out this makes sense. It turns out in the code, the rod is going to be a list of items. The first item in the list corresponds to rod with a 0 there. So that's why my increment parameter is starting here at 0. That means we're going to need to change our center of mass formula just slightly. Instead of going from from 1 to n, we're going to go from 0 to n minus 1. And that's going to be on both of these here. So I apologize, but this is just trying to make sure that we're not n minus 0. That's going to go to n minus 1, right? This will match up to the convention in Python of the first element in a list being 0, not 1. So that's what we're doing for all that. So that's what we're trying to do. We're trying to use calculus, and then we have to change it back to discrete land so that we can do this. Let's clear out those drawings for a minute. All right. Next, so notice I do not want to use less than or equal here. I want to use less than because the first value is going to be 0. And then it's going to go through the while loop and do a bunch of stuff. And it's going to keep going. And notice n minus 1 will compute. But as soon as we hit n, that's 1 too many. And it won't do a calculation for n. So this is basically a way to write for I equals 0 to n minus 1. Now, just so we can see these on the screen, I'm going to lower this rate down for a minute. This just says how many frames are displayed per second. So we should see some change on the screen approximately every half second. Now, I'm going to draw a ball. And so you might not have this in your starter code, but I'll just let you look at it for a second. The idea here is we're going to draw a sphere. And then immediately afterwards, I'm going to specify its position. And this is where things get a little bit tricky. We need to think. All right. So I know it's going to be a vector. And I know I need to build the rod out of spheres. So I know each sphere in here needs to have a slightly different position. They can't all have the same. And it's probably going to relate to this parameter I. So here is one plausible way to do this. Sorry. Let's go right here. The vector should equal, let's say we know it should be at I times dx, right? Comma 0, comma 0. Now I could start right there. And what would this do? I need to draw this a little bit. So if I could, our visual guide was a cylinder. Okay, our visual guide was a cylinder. And remember, the position attribute of the visual guide cylinder is right there at its left end based off the axis we chose. Great. Now, if I draw a sphere at that same position, it would be located right there. And notice the sphere, half of the sphere would be outside of the rod. Now, this could get us approximately correct, and it would work, but it sure would be nice if we could just shift it over by this distance. Well, that distance is, we're going to call that dx over 2. Right? So I want to shift it over half a unit. So in this case, I'm going to say plus dx over 2. By doing that, and you could be clever here, I guess you could say, you could write this as what? Dx times I plus 0.5 might be another way you could do that. Something like that. And that maybe reads a little bit cleaner, but there's lots of different ways you could do that. For me, I don't know why. It just makes sense to me to say it's I times dx plus dx over 2. So I could read that and it makes sense to me. I'm like, okay, the first one, when I equals 0, gets shifted over by half of the dx. The next one, when I go through this loop, it's going to be I will increment at the end of the loop. So I would be 1. It'll shift it over by 1 unit of dx. And what this loop does is it's going to keep going through here over and over and over again, going through every value of I, and it'll draw a ball at every value of I. Cool. Next. So let me clear this out here. Let me clear out that annotation. Sorry. Next, I'm going to create a new attribute called ball.dm. In this case, I want to get, right, dm, if you remember from calculus, in general, dm is equal to lambda dx, or density times dx. Now today I've chosen to go with mu. All right, so we're going to say mu dx. So in this case, we're going with mu star dx. Sweet. All right, so that's it. This will get me the mass. Now think about this. If you cut this thing up into smaller and smaller slices, if you use a higher value of n, dx gets smaller. Remember, dx was right here. So if we go back to this, if you use a smaller value, a larger value of n, you get a smaller value of dx, and each mass would be a little bit smaller. That's cool. All right, now this is where we get kind of interesting. Rod was a list. And what I want to do is this line of code right here. So this says append to the existing list the object inside of here. So now in this case, rod was a list. To remind you, rod was declared like this with these square brackets, and it had nothing inside of it. This says, okay, put this ball inside of it, including all of the attributes associated with it. First, you might be saying, this is silly. There's reasons to do it. Just trust me. Okay, next. Now I want to get back, and I'll try to get this back on our screen again. I'll just remind you, remember, we're doing the sum from I equals 0 to n minus 1 now of basically the radius sub I, or x vector sub I, or whatever, times mass sub I divided by a similar sum, except with just the masses. All right. So in this case, right here, what are we trying to do? Let me scoot down 1 unit. There we go. So here, I'm going to reference this in a strange way that we haven't done before, just so you get some practice. Rod, whoops, I'm going to say the numerator. I need to add this into the numerator. Oh, I don't want this to equal the numerator. I want it to add it to the numerator. So when I add it to the numerator, this says, take the existing numerator and add to it. Well, whoa, that's not what I want. The existing numerator was a 0, 0, 0 vector. Well, what I'm going to do to it is I'm going to add the ith element of the rod and get its position. And I'm going to multiply that by the ith element of the rod and get its mass. So this line right here is the numerator. It's doing one line of the sum at a time, and the plus equals says the next time you go through the loop, add the next one to it. The next time you go through the loop, add the next one to it, and you just keep going and going and going. Similarly, the denominator, I need to add to it just the rod's mass. Okay, so in this case, again, what are we doing here? Whew, let's digest this. This line says, okay, take the existing denominator, which was 0, and add to it the rod's ith element and get that mass of that ith element. So it says, okay, look, right now in the first time through the loop, I equals 0, go to the 0th element in the list, find its mass, and add that to the denominator. Whew, that's good to go. And then finally, we're going to increment this. Cool. So this is the line of code doing the physics right there, or the center of mass. Great. So now I'm going to run this really quick and see what we get. There we see the balls being drawn. And notice there's a little bit extra there. You might be saying, whoa, how do you do all that? Well, I'll just mention some things here. Whoops. If I scroll down a little bit, and if I maybe make this a little bit smaller so I could see more. Sorry, whoops. I'm zooming in just so we could see all this at once. All right, that's pretty good. So notice it drew 5 balls and then it drew this pink marker there. And I actually did some calculations here I had it spit out the total mass and the center mass. So before I show you how to do it, you could pause the video and think, how did I do all that? All right. Now let's go take a look at it and see. So if you want to go take a look, okay, so this was all doing that. Now, how did I output the total mass? Well, remember, that's just the denominator. So I just printed the denominator. Now, what should the mass be for a for a uniform linear mass density? We expect mass total should just be density times the rod length. Well, that was mu times the rod length. So I have the code do it for me rather than working it out on paper and just hard coding it. Now, if my rod length changes or whatever, or if my mu changes, it'll still get the correct mass. Now this percent difference is calculated. Now here, remember, the denominator is essentially the total mass. So it's the code's total mass, which is like the experimental value, minus the theory, divided by the theory times 100%. And then I spit that out. How did I do the center of mass? Well, in this case, the center of mass is the numerator over the denominator. Got it. And I could print that out. And then I just drew a center of mass indicator. That was this sphere of this color. And I just said the position is the center of mass. And then I just made the radius fit the visual guide. So far, so good. What should the theoretical value be? Now look carefully here. You could say there's easier ways to do this. You could have just said it's rod length over 2. However, I chose to do it this way. So I take the center of mass x coordinate should be the visual guide's position x coordinate plus the length over 2. That way, if I choose to move things to a different spot on the screen, this percent difference should still work. Now, and then I do my standard percent difference again. So it's experiment. And now notice I'm just getting the x component here. So I'm doing a scalar, right? I'm not doing the whole center of mass vector. I'm just getting the x component of the center of mass and subtracting off the theoretical x value of the center mass, dividing by that. Okay, cool. And I print that out. All right, so that's how I got all those. Now you might ask, man, I don't like having to constantly retype that percent difference. Isn't there a better way? Turns out you could define a function called pdiff, all right? And you could tell it the inputs. It's always experiment minus theory, so why don't we just say x experiment, comma, x theory. And so this, whoops, let me put a colon here. All right, so what I've done is I've defined a new function called percent difference, and I've told it that I should expect 2 inputs. One should be an experimental value, and one should be a theoretical value, and I've given them these names. All right, and now what do I want it to do? Well, it's we could tell it to return the following. We could say it's equal to x experiment minus x theory divided by x theory times 100. And so, great, now I'm done with that. Whoops. All right, and so what we could do, let's see if this works. So what I'm going to do is I'm going to comment out, actually, let me do this. Let's make a copy of this. And oops, we'll put it down here. And then I'm going to comment out these lines of code. So I want to see if my new function works. And then let me do this. I'm going to say, okay, I want my percent difference to equal the pdiff of the experimental value was com.x, comma, and then I need the theoretical value, which was comx underscore th. And so let's see if we still get the same value here, right? So hopefully I didn't make a typo. There's drawing the balls. We get this locator, and then I'm going to scroll down a bit, and I'm going to make this smaller. I could zoom in a bit, but you could see it there one more time just so you could really see it. And notice we still are able to compute the center of mass. Now, some weird things will happen sometimes. Notice this is getting the answer perfect. This is not always going to get the answer perfect. What if I do 5.134 and maybe change this to 7? This is why we coded it, well, in all these weird ways. When we do this one now, I should have sped up the rate. So at this point, if you get tired of this going so slow, you could speed up the rate. But when I scroll down here, notice we start to get some weird numbers for the percent difference. So this can happen occasionally, but let's look into this one. Blah, 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 blah. E negative 14. What does that mean? It's a number times 10 to the minus 14th. So that's a very, very, very small percent difference. It's effectively 0. So that's some rounding errors in the calculations in the code. Basically, it's still looking pretty good. All right. So let's see. I've told you pretty much everything I want. So that function trick could really be useful. Now there is one more thing I want to